So first of all, I want to thank the organizers for creating this meeting in honor of Volodya, and thank you for allowing me to participate. I knew and followed Volodya's career since, at least since he came to Harvard, but I met him earlier. And I always considered him a friend, as well as a fantastically gifted mathematician. So I'm going to talk about mathematics I hadn't thought about for 15 years. And it's sort of interesting. I'm grateful for the opportunity to go back and then see it in this context, because it enables me to see Volodya's work to show why it is so important in comparison with efforts some of us were doing at the same time. And I'm a little aware of the time because Nadia occasionally asked me, when was this, when was that? And I never looked back to see how things were doing. Volodya was even my colleague for a year. And we were sort of working in parallel tracks, but we didn't actually sort of exchange that many ideas. And what I'm about to discuss began, I looked up my first paper on the subject was submitted in 1989, so that shows that was when Volodya was still in Moscow. And there's some similarity here, but I think that the differences in the depth of Volodya's work is really, really quite interesting. And it's not true that people didn't use algebraic topology or homotopy theory in algebraic geometry, or didn't try to do it. Many of us were trying to do it, but in not with the ambition and the depth that Volodya did. Volodya sort of took seriously, I think, the idea of motives and Valencin's point of view, and tried to basically reconstruct much of the world of algebraic geometry embedded in homotopy theory. And speaking for myself and other people, we had a much more limited vision, and you'll see that limited vision. We were trying to look at targets and get invariance or something, but we didn't try and model the entire world of algebraic geometry. And what Volodya did is truly remarkable and special, and I think especially Mike's lecture shows how once you adopt and adapt this point of view, and if you have a homotopy theoretic background, it's very profitable. So let me begin by a little background. I was interested in the 80s in algebraic K-theory, and I was trying to find a simpler reflection of it in topology. So I developed something partly with Bill Dwyer called atoll K-theory, and that was supposed to be a topological version of algebraic K-theory that you could compute. And I viewed that as sort of a failure because it turns out that basically atoll K-theory with finite coefficients is isomorphic to algebraic K-theory. So what I wanted was something simpler and computational. And it's interesting to come up with a completely different construction and then show it's the same as something you'd like to study, but it wasn't really, it didn't give that much light or much light into algebraic K-theory. And then, so I was looking for something that was a little more connected with geometry, wasn't going to be the same as algebraic K-theory in some sense. And Blaine Lawson proved a remarkable theorem, the Lawson suspension theorem, and Barry Mazur connected Blaine and myself. And that was the origins of this theory I'm going to talk about. And what I'm I hope I get to the punchline of this theory, which is that it's crying out to be developed the way Volodya would have liked to have done. And I see various pointers of the way you would find you're on the right track. But together with collaborators, we sort of came to a stop about 2004. And so maybe now is the time to revisit this. And you'll see that there's a lot of depth in this. I'll probably hide the Hodge conjecture, the generalized Hodge conjecture, but we'll see the Grotny standard conjectures, and we'll see other aspects that are wrapped up in this theory that it's not clear at all whether it provides any roadmap into addressing some of these deep questions. But the theory looks good. So basically, and I've got four versions of this, and it's going to really confuse me. I keep rewriting it. So this one is the beginning of an outline. But basically, we want to start out with algebraic K-theory. So we'll take X, at least for most of this talk, quasi-projective over the complex numbers. Sometimes it'll be smooth. And this will be some nicely chosen spectrum representing algebraic K-theory. Now, equality here is really significant. There are all different sorts of models for this. And I interchangeably use many, many different models. But basically, I'd like it to be a spectrum in the sense of algebraic topology. We'll see. And then I'm interested. Pardon? It's not a homotopy function. No, we can construct an infinite loop space whose homotopy groups, yeah, as a spectrum. Variety? Pardon? It is a spectrum attached to variety? Yeah. Yeah. Now, to what extent? Well, I guess we know it. We can pin it down as a spectrum, but yeah, it is a spectrum. Spectrum in the sense of algebraic topology attached to a quasi-projective variety. Not necessarily complex over the complexes. Yes, the pi I or the, and the pi I with Z mod n coefficients.
The homology, the spectrum, the algebraic K-theory.
Yeah, but so we're going to see in the board underneath, you'll see a little bit more of that. I mean, but the one advantage of this is I can look at mod n coefficients, for example. So it's not just. Right. And then on this side, I'm going to have something which I'll call K top of X analytic. X analytic is the underlying analytic space, and K top is connected K theory. I mean, that's probably a bad symbol for this. I could look at little ku or something. And what this theory that we'll see, and we'll analyze it a bit, goes in between. So we'll call this K semi. These are all spectra. And let me heuristically say what's going on with these constructions. No. No, it's very interesting to look at K0. So, semi-topological. So, in some sense, this is obtained by looking at morphisms from X into Gauss-Monians. We can make this formal with some infinite loop space machine, operad, Siegel gamma spaces, or whatever. These are morphisms of varieties over K. I'd like to. Equal to what? That's the K of X? Pardon? This is going to be, that spectrum will be obtained out from this sort of data. So you, in fact, could be a little bit more precise. I'd look at, let's say, codimension D planes in P infinity for various D, and then build some construction out of that in an infinite loop space machine. And this space is built out of a similar thing. We can look at continuous maps from X analytic to, again, to Grassmannians. And this already inherits a topology. This we need to, in some sense, as it stands, it looks like a set. So we can make it at least a simplicial set in a very standard way by looking at something like x dot delta dot. Now we're in the land of, if you want, homotopy or topology. So we promote this to here, and we get the spectrum after we do some machinery. And here we already have a spectrum. And what goes in between? What goes in between is, so excellent Blackboard style, it doesn't fit, will be morphisms from X to Grassmannians. So just like for algebraic K-theory, but we're over the complex numbers, we give this a variety structure, and we take the analytic type of this. So we take the homotopy type. So think of this as morphisms from X. Maybe X is projective if you want things to be finite dimensional from codimension D linear cycles in some bigger projective space. Then that's a variety, and we can look at the analytic space over the complex numbers. We get a topological space, and we construct, again, we get, because of machinery, we get a spectrum. And that's what lies in between. So this is built by looking at algebraic maps from X into Grassmannians. This is built by algebraic maps from X into Grassmannians, but with giving the maps the analytic topology. And this is built by continuous maps from X to the analytic topology. So what do we know? We know some things about this. And this will motivate some of what I want to say.
First two homotopy equivalent.
No.
Looks like the singular complex of that one is that one.
No, these are algebraic. No, it's very different. So for example, if we take X to be the spectrum of a field, then we get the algebraic, the homotopy of Kx is whatever this is, the K theory of the field. So just for example, K1 of the field is some very large group, which is, at least I can give no meaning to. Whereas these two, where did I put the semi? K semi, and I think I wanted the top down, but anyway, K semi, when X is spectrum of a field, is homotopy equivalent to K top. It's homotopy equivalent if X is complex numbers, if X is a smooth projective curve. We have various computations. So one thing that shows you that there is some interest or subtlety is what's going on at K0.
Sorry, in the K top term,
Yeah.
The complex structure of X plays any role?
Yes.
Yes.
Well, analytic means you take the complex points and you give that the usual analytic topology. So please.
Just the topology of X.
Just the topology of the analytic points.
So it is rather X top, yes?
Yeah.
You get
No, no. So what happens at pi naught?
But Eric's question was what role is played by the complex structure? And none, it's just that gives you trends.
You mean here? Oh, not the complex structure, but the complex points, yes. Yeah, no, I'm not. I'm just looking at the analytic topological space. For pi naught, we have the, so I'm covering up a board here. That's why this is awkward. For pi naught, we basically have, and this gives you the intuition of what's going on, algebraic vector bundles over X modulo isomorphism or something. Gives you K naught. This is for K X. For K semi, we have algebraic vector bundles over X modulo algebraic equivalence of vector bundles. By which I mean if we have two vector bundles, they're going to be algebraically, make this into equivalence relation, E is equivalent to E prime if you have a smooth curve and a vector bundle over the curve and 2 points, P1, P2, and smooth connected curve. So you're just replacing A1 by any smooth curve. And then topological vector, pi naught here we didn't change the objects, we changed the equivalence relation. And when we go over to here, we change both the objects, they're topological vector bundles, more objects, and the equivalence is topological equivalence. You can put a unit interval here and make the same. So that's the map. So that's sort of the context, and the context is to sort of construct, if you will, this I cannot do, is to construct a theory where I'm replacing A1 by curve equivalence. I didn't start out trying to do that, but I would very much like to do that. So I wrote this down before you came in because I thought it would save a little time. There is some real content in this construction. And the symbols aren't really defined, but we have the motivic spectral, so I should say X is smooth. Quasi-projective over C. This is the motivic spectral sequence. And we could replace this with Z mod n coefficients, which I may want to do. This is the Atiyah-Hirzebruch spectral sequence. And one reason I wanted to write this carefully is I can never keep track of the indexing. This is a usual D2. So Andre Suslin and I wrote down a proof of this motivic spectral sequence, and we could never remember, even Andre, just this indexing, but I believe it's correct. But in any event, they're compatible, and we have this map of spectral sequences. So this guy, I want to explain this before I tell you some of the properties of the spectral sequence. So this is where Blaine Lawson's work comes in and is part of the motivation of creating this intermediate thing and thinking that it might be good. So Blaine Lawson introduced something which eventually became, we called Lawson homology. So it's in homology, so I'll write it somewhat differently. LRHN of X. And this is still for X over the complex numbers. And what this is this is it took a little while to interpret this, and I guess it maybe involved work of Ofer Gaber and myself. Oh, I should have mentioned that this background, maybe I better look at the list of co-authors, involves Blaine Lawson, Ofer Gaber, Barry Mazur, Mark Walker, Christian Hasemeyer. It's collaboration with all those people. This is, by definition, it is the homotopy groups of the algebraic R cycles on X. This is our friendly algebraic R cycles on X. But the trick is, and that's the weird thing that's coming on in here as well, in this semi, we're taking, these are algebraic R cycles. The objects are the same, but we're putting the analytic topology on the R cycles. So this is a really strange thing. It's a hybrid. So there was a similar hybrid when we worked with étale things as well. And now you might say, why is there any sort of topology, analytic topology on R cycles? And R cycles on X, let's say X is projective, just to simplify matters. R cycles are some sort of group completion, and often a colimit, but let's say group completion of Chow varieties of R cycles of various degrees. D is the degree of X, say, embed in Pn, and this is the degree with respect to that embedding of R cycles on X. Now, this is an algebraic variety over the complex numbers. It has an analytic topology, and this, all of R cycles inherits. You take some sort of group completion and give it the analytic topology. So Blaine proved a remarkable theorem about this, which got it going. Otherwise, it would just be sort of a nutty idea. And I wanted to explain this. Blaine and I built a companion theory. So there's the cohomology theory. Let's just say LSHM of X. This is homotopy, again, of cocycles now.
That notation, LSHM, what does that mean? Just,
It's L for Lawson, so I introduced it.
it just means that's one thing with two.
Yeah, it's double indexed. It's just like motivic. It's double, and the indices are double indices, and we're going to see that these are very, very different. On the other hand, these are all equal. Convergent spectral sequences. I'll explain that in a moment, but there's a real, even though the abutments look very different, well, I'll come to that in a moment, but it's all one entity. So the homotopy groups here are, if it's HM, this is pi 2s minus m. And these are cocycles, so we define these geometrically, algebraic cocycles. And what Blaine and I proved is if X is smooth, then this is isomorphic to LD minus S, H2D minus M of X. So this is the cohomology theory that for smooth X is, we can think of as the Lawson homology, and this is the E2 term of a spectral sequence that abuts to this semi-topological theory. Mm-hmm. No. So this was, not all cycles pull back. So it was my intuition that what are nice cycles on X that are sort of behave with respect to contravariance? Well, they're ones defined by, let me get this right, maps from X to, well, let's just say 0 cycles on PS. That's what, but by Lawson's suspension, we could increase these numbers and play around with them. But so this is an effective cocycle of degree of codimension S. So, and in fact, there's a good model for the Eilenberg-MacLane spaces if we wanted to PS minus 1. But these are morphisms into, this is the Chow monoid to make it effective cocycles. So So I'll just explain a little bit more about why these are good. So if you have, as one often does, into any, let's say PR, like that, then one gets inside X cross Pn, n minus S, I guess, a codimension S cycle. Now this codimension S cycle, this Z, is contravariant in X. If I have X prime to X, I just compose. So Suslin Voevodsky wrote a paper about, I've forgotten what they call it, good relative cycles. But at least in characteristic 0, it's basically what we were doing, maybe, these contravariant, they're not all, the Chow variety does not represent cycles, so, but it almost does, and that's what this is. Okay, so now let's go back to this picture. We'd like to understand something about algebraic K-theory. So topological K-theory is a very weak target. Now what Voevodsky would say is you go back and you redo all the, not the foundations, but you put it in a world where you can play with it. What I was doing was trying to find a target where I could understand something better. Now, this becomes an isomorphism when we replace Z by Z mod n. So this is an isomorphism So just in pi naught, that's a statement about the Chow variety mod n and algebraic cycles modulo algebraic equivalence mod n. And this becomes an isomorphism if you invert the Bott element. The Bott element lives in this K-semi world. It doesn't actually live in the algebraic world. So this theory sits in between algebraic K-theory and topological K-theory, and it has various good properties. But let's look at it a little bit more to see about approximation. My goal, which really isn't satisfied, is that this theory would be much more computable, or if you want, this theory would be much more computable than the algebraic one, than motivic homology. Now, first of all, because this is an isomorphism mod n, all the interest is in looking at rational coefficients. So we'll look at rational coefficients.
Is this Bott element, when you look at it mod n, you've got Thomason's Bott element?
Yeah, prop mod n, it becomes Thomason.
So you recover his isomorphism by combining them.
I suppose, but we prove just directly that, yeah. We don't actually, maybe, we don't use Thomason. Yeah, I guess we do. I never thought of it, but I guess we do. I didn't want to claim.
The little guy is not finally generated, but you're saying you invert Bott element is finally generated?
Yeah, so Chuck just jumped to one of the things I wanted to say is if we look at, another thing is if we tensor with Q, all three of these spectral sequences degenerate. So then we could, instead of looking at the K theory, we can look at the cohomology theories. Okay? And I am much more comfortable in the indexing looking at homology than cohomology. So what I'm really interested in, if you want, is the behavior of LRH and of X. Let's put the coefficients on the inside or outside. But to understand this, maybe we'll put the coefficients on the outside. Sometimes we'll look at it with Z. So what Chuck observed is just in pi naught here, we're taking, this is, as I said, algebraic vector bundles modulo algebraic equivalence. The Griffiths group can be infinitely generated. So this is not necessarily finitely generated. In particular, there's a kernel here often. And the Griffiths group is not finitely generated even when you look at rational coefficients. So we're not helping matters. So this is most definitely not injective, but of course it's not surjective either, tensor Q, because not all, we've just heard that there are conditions to algebraicize, for example, Chern class conditions, to say that a bundle is comes from an algebraic vector bundle. So these are not isomorphic at all. But my intuition was, and it's never been really justified, but my intuition was that this would retain the geometry of X and get rid of the arithmetic. I was always sort of puzzled, like, what is K1 of C star? And at least from, I don't know, from a topological view or whatever, C star and the higher K groups, even the Milnor K groups of C star, are just enormous, and they don't seem to, without more structure. What it is an incredibly large, we know the cardinality of the rational vector space plus a Q mod Z, but that doesn't tell us anything. Well, all of that vanishes here. And in fact, I've sort of conjectured that these groups are not infinitely divisible, and maybe what you're doing is getting rid of the infinitely divisible stuff. But Nori told me that he had almost the opposite thing, conjecture in a different context, so I don't know if that's true. But in any event, the idea was that these groups would capture some of the geometry. For example, you see the Neron-Savary group here just in pi naught, and would get rid of a lot of the arithmetic. So where am I in this pattern? So I'd like to mention something that Volodya introduced in this context. Which makes, heuristically, I still think of this construction as the, where is it? The space of continuous, the space of, up there, the space of morphisms with the analytic topology. But Volodya made the following suggestion, which made a lot of which improved matters tremendously. I made sense of this. I wanted to make this a topological, a simplicial set. At the moment, on the top line, it was only a set. You do that by inserting a delta dot here. I didn't need to do that here, but I could have. I could have put a delta dot top here. Now, Volodya suggested to look at morphisms, algebraic morphisms of complex algebraic varieties of X cross delta dot top. To Gross, for example. By the way, there's similar definitions for the cohomology theories as well. You have Eilenberg-MacLane models, and you can look at algebraic maps and then take. So this is the ingredient, or this is the input for K semi. And this is fine, but it doesn't make any sense. So what sense does it make? So this was Volodya's suggestion. Suppose we have a presheaf on, I don't know what, schemes over K, schemes over C. Maybe just a set. We can take the Kahn extension and extend it to topological spaces. So we look at the extension. I don't know what this is. This is a adjoint. If I change of sites, I guess it's epsilon lower shriek or something of F. To, well, let's let epsilon be the map from the analytic site of X to the Zariski site, for example, of X. So we can take the Kahn extension and extend this functor to a functor on spaces. So what this is the simplicial set, which in degree D is morphisms from X cross delta D top, which is just the D simplex with its topological space into Gauss. So what do we, just to make it explicit, what are morphisms from X cross delta D top for some D? Gauss. Now I could have put any pre-sheaf there. Well, they're the co-limit. We're looking at the functor where this is variable. The co-limit as from delta D top to U analytic, this is just how you build this Kahn extension, of the functor applied to more cross U cross. What did X cross morphisms of X cross U dot. Sorry, this has become illegible, but I'm sure most people understand such adjunctions better than I do. So there's just a canonical way to extend this Kahn extension. You have a functor on a pre-sheaf on here, and you can extend it to a pre-sheaf here. So this looks good. Now, Mark Walker and I proved a theorem that's very much inspired by a similar result that Volodya proved. So, which enables us to, for example, to show that this degenerates rationally. In fact, it gives another proof that this is an isomorphic Z mod n, and allows quite a few computations. And this is really due to Voevodsky, although he never looked at this semi-topological business. So suppose you have a map of pre-sheaves. Somewhere. Zariski pre-sheaves. Now, Voevodsky introduced, I guess we were told, 3 topologies, never counted, but one of them is the H topology. And suppose this map of pre-sheaves induces an isomorphism of sheaves, associated H sheaves. That implies that F delta dot top, okay, this is a simplicial set. If we have a group structure on values, then we're going to get some sort of simplicial abelian group. But that implies that this is an equivalence. So this, what Mark Walker and I call recognition principle, turned out to be very valuable.
And the top means to do the Kahn extension you mentioned before?
Yeah. I mean, here we have the associated H sheafification, and then you just naively apply. It's the naive. Goes back to what Pierre asked. You take the naive functor and apply it to this delta dot top. Okay, so I wanted to introduce another feature that I think is very special to the semi context. And this arose in work of Barry Mazur and myself. And it's a very simple consequence of eraser. I was looking for a squishy. Very simple consequence of Lawson's main theorem. And I'll state it in homology, because I can keep the indices straight, but if we're working towards K-theory, we maybe should switch to cohomology. So this is the homotopy groups of R cycles. And Barry, Mazur, and I showed that there was a very natural map called the S, we called it the, I have no idea, I can't remember why we called it the S map, from the homotopy group of R cycles to the homotopy groups of R minus 1 cycles. So I don't know a corresponding thing really motivically. And the proof, let's see if I can get this. Just you look at R cycles, and you cross this with P1. And you take an R cycle and a point, and you get an R plus 1 cycle on X join P1. That's a fairly naive construction. And then Lawson suspension says this is equivalent to R minus 1 cycles on X. Well, we interpret this as the adjoint of a map from ZR of X. And one could do this in the A1 category. I don't think it's been done, but the adjoint of a map from R cycles to loop 2 on R minus 1 cycles.
What's that, X, something P1 mean?
Oh, you look inside, you embed both of these, and it means join. You look at all lines between points of X and points of P1 when they're suitably placed.
Complex lines?
Yeah, yeah.
That loop 2 is P1.
It's the P1. It's the P1. I mean, this really goes through smash if you want.
So it's not fine.
No. Why? Oh, it's. This is a projective variety. Okay, so we have this map, and one of the things Barry and I proved was the R-fold iterate of this map from Lawson homology to the L0 Hn of X.
That's equivalent to homotopy equivalence?
Yeah, it's non-canonical. There is actually a homotopy equivalence. Yeah, and
That's the remarkable theorem of Lawson.
that's the remarkable theorem of Lawson. There's another. I think of this as basically Dole-Tom, but in any event, this is just ordinary homology of X, the singular homology of X. And Barry and I show that this is the cycle map, whatever the cycle map is. Okay, but one interesting thing is now the cycle map is a composition, an R-fold composition. So because it's a composition, you can look at filtrations with that composition. So I should have had another prepared blackboard, but I did not. Maybe I'll get rid of the spectral sequences and put it here. We have various computations of this, but I want to get to where this should be going, so I'll just explain the relationship to the standard conjectures and then go on.
Does that S comes from a map of spectra?
You know, the way I would think of this is I have topological Abelian groups. So yeah. I mean, you can give it the structure of a map of spectra if you wish. Or, I mean, you might just want to do it in the derived category and just do it on complexes. But it's not just, you know. Okay, so let me introduce filtrations on homology. And I should probably, for these conjectures, assume X is smooth. There was no assumption of X being smooth here. But the first filtration is what Barry and I call the topological filtration, and I may have the indexing wrong. This is the image of S R, LR, H and X. The second we could call the correspondence filtration. So we show how you get using this Lawson business, it turns out you don't need correspondences between smooth varieties. You can construct correspondence maps in homology with singular varieties, but assuming smooth, it's even better. This is classes in the image of a relative dimension R correspondence. Then, I don't know how much slower I can go, we have I'm not sure what this is called. This is the dual of Grothendieck's Code-Nouveau filtration put in homology. This is the classes, the span of the classes generated, maybe we need rational coefficient, span of the classes generated, if I've got the indices right, by how do I want to say this? You know, Grothendieck was also looking at correspondences. I'm trying to distinguish. I'll give you the punchline, and maybe I can feed back what Barry and I proved these are the same. These are this is Maser. The equivalents of these are this is equivalent if and only if the standard conjecture B. And then, now what am I missing here? These are the images of correspondences of classes. Maybe there's a condition on the, maybe this is the let me flub this, and I can do it later. And then there's one more. There's the refined Hodge filtration in terms of width. And Barry and I, I guess in something in 1991, 92, conjectured that all of these are equivalent, and we didn't realize at the time this involved the standard conjecture.
Are these all subgroups of the same group?
Yeah, HN.
So you mean equal?
Yes, equal. Thank you. Pardon? No, we know what equal is, we don't know what the same is. Okay, let me finish by not worrying about this, my confusion with Grothendieck's versus this correspondence thing. Let me skip all calculations. Oh, I was also going to tell you about Sussman's conjecture. Maybe I'll say one aspect without even stating Sussman's conjecture. Suslin's conjecture is the combination of showing these are the same, so that's equivalent to the surjectivity aspect of Suslin's conjecture within an injectivity statement. And I just want to mention this injectivity statement because we have no idea at all how to approach it. And this is an analog of valence and Soule vanishing. But you can think of it as with rational coefficients. So if you look at pi n, no, maybe I'm looking at pi I of zr of x. We conjectured that this would be 0 if I plus 2r is bigger than twice the dimension of x. Now, the best reason to think this is true is if you flip the indices, this is saying that the negative, that the cohomology vanishes in negative degrees. It's a stupid nomenclature. But it's really very plausible to do this. And in fact, I think, while Volodya was still at Harvard and he visited me at Evanston, we talked, I was challenged by, and I still have no idea how to prove this. How do you prove that pi I of 1 cycles on a threefold are 0 for I very, very big? Even for a triple product of elliptic curves. So the answer is you fit them, the only way I know how to prove vanishing of homotopy is you put things in long exact sequences. And we understand what's happening to divisors. So you're very tempted here to say 1 cycles on a threefold, they correspond to 1 cycles on 2 cycles on a threefold, and it's a compound divisor or something. I don't know. So there's another aspect that Suslin conjectured that implies this vanishing, which we don't know. Okay, so the point of the talk, which will be given in like 1 or 2 minutes, is the following. The first point of the talk, I don't know if I have to write anything down, is that there should be some sort of site that incorporates this delta dot top. There should be some motivic way to do this. But what I'd really like to do is do it over fields other than the complex numbers. And I don't know how to do that. Mark Walker and I did it over the reals, and we have a theory that has every theorem you can prove for the complexes, it has an analog for the reals. For the reals, instead of mapping to, it maps to Atiyah real K-theory. But it's the theory mod n is isomorphic to algebraic K-theory for a variety of the reals. But we don't know how to go beyond the reals, because for the reals, we really need the analytic topology of real points. And in particular, we need the analytic connected components of the real points. And this figures in the computation of the algebraic K-theory of a ring or a variety over the reals. And we don't, so there are lots of other contexts where you have a topology. And, or you could look at, for example, it'd be very natural to look at varieties over C adjoint variable, for example, or look at p-adic fields. But I don't know how to do this delta dot top at all. And I think if one had some sort of, let's say, Voevodsky way of envisioning what's going on here when you're doing this delta top business, then at least you could do it for other fields, and it might feed insight into this. So,
An arbitrary field?
I would take any field other than the reals and the complexes. No, I don't know. And then what properties, I'll conclude by what properties would you like? I mean, K-semi has nice properties. What would you like? Well, one thing I'd like is that if you had, it should be behave well with respect to base change from one field to another. Otherwise, why vary the field? But another, I think I want that if I have an extension of algebraically closed fields, then the theory doesn't change. This is what happens with algebraic equivalence. You certainly want that with mod n coefficients, it agrees with motivic theory. So that, you know, there's a design about where you want to go, but there's no path. There's no Voevodsky to lead us along the path to get there. Okay, I think my time is up. Thank you.